Okay, gravitational potential energy is an example of this this equation being remodeled somewhat. So if we consider a planet, let's say Earth, and we have some mass on it, it's a pretty big mass, you can see it from space, but there you are. This mass has got obviously a weight, and the magnitude, the size of that weight, is given by the value mg, mass times by gravity. Okay, now if I then want to lift this thing up, displace it, let's just take it upwards in the gravitational field, mg. Obviously on this scale gravity wouldn't be constant, but assuming it was, then the force required to overcome gravity, assuming I did it infinitely slow, I just got to be equal to mg and then a fraction beyond it, and super slowly took it up. I could see the force to overcome gravity and lift it up to this height h would be given by mg. Okay, and the distance that I would travel, instead of writing delta s, we would call this displacement the height. So it's simply the force times displacement in the direction of the force. Okay, now in this case we're overcoming gravity, which is why it's a bit, we still say gravity. This is the work done on the system if we lift it up, and it's also equal to work done by the system if it falls down. Now later on in A2 you'll get your brain thoroughly squeezed when you find out that it's all negative, but we won't go there now. So it's basically work done is mgh, and it's basically the force overcoming gravity. Now it's important to know this, that at GCSE you'd say, oh, Johnny lifts a ball 2 meters and the ball weighs 2 kilograms, how much GPE does the ball have? It's all good at GCSE, but it's worth noting that really if the Earth wasn't here, then this thing wouldn't have any gravitational potential energy in it. So I don't know if you could somehow blast an Earth away and make it disappear, but if it was there and it had gravitational potential energy and we vaporise the Earth, suddenly that energy would cease to exist. So the GPE doesn't belong to an object, it belongs to the system of masses, and it basically exists but due to the separation of the mass and the Earth. Okay, and it could be a planet, an object, normally it is, it could be a pair of planets, it could be whatever you want it to be, but it belongs to a system of masses. And so this statement here is just a little extra that you need to be mindful of if you're taking this at A level. So we've looked at gravitational potential energy, and we now need to think about kinetic energy. Everyone, I hope, remembers this equation from GCSE. Kinetic energy is a half mv squared, and people often think about it as basically the energy that is contained in a moving object, but really you've got to think of it as the work that is done when you're accelerating an object. If you consider an object that's stationary, you apply a force to it, the object starts to accelerate in the direction of the force, you remove the force, the object keeps going unless acted upon by some external force, Newton's laws. It's all good. But if you're applying a force to make it accelerate, that force must apply over a certain distance, and therefore a measurable amount of work must be done, because when you apply a force for distance, we get the old equation, work done, force times delta S. So if you apply a force for a certain distance or a certain displacement, you're doing some work on it, and this really is the basis, just like with gravitational potential energy. This is in fact the root of the kinetic energy equation. So there are loads of different ways you can substitute all sorts of ways to derive this equation from this, but let's just think of some easy ones. Let's think of a suvat first. V squared equals u squared plus 2as. Now if you just understood what I said there, that the work done accelerating an object from rest, okay, is the kinetic energy, then we can imagine that we can get rid of the u, because from rest the u is nothing. Okay, so we can rearrange this and say, well, v squared over 2, oh look, v squared in half, that's easy, is equal to as. That's grand. And then let's think force. Well, what is force? If we think to Newton's second law, we can write F equals ma. That's pretty handy. that will work for us, won't it? So if we substitute this bit here in for the force, we get work done equals ma. Okay, and then let's think to ourselves ma times delta s, that's that bit there, and then let's think, oh, over here we've just established that a times s, the distance travelled, this is delta, the distance moved, forget about the delta, but a times s is a half v squared, or v squared upon 2, so we can simply get these two, and that gives us v squared over 2, which is of course most commonly written as a half mv squared. And so you can do that using that, see that you can use it, do it using, you can do this from about 50 different ways. Maybe that's an exaggeration. You can do it a lot of ways though. So what the take home message is that kinetic energy, KE, is a half mv squared, and it is the work done in accelerating an object from rest. I should really put note of that, from rest. Okay. Okay, we've seen gravitational potential energy, we've looked at kinetic energy, and now it's time to put the two together. So when an object falls, its gravitational potential energy is transferred, converted, transformed is the word I'm looking for, into kinetic energy. Now, if there's friction and stuff, it's not 100% conversion. Eventually, it would reach terminal velocity, and it would all just be getting, as it falls at a constant speed, it would just be turned into heat due to friction. But over a small distance, you know, a few meters, we can pretty much assume it's 100% conversion, which means that we can say the gravitational potential energy has turned into and is equal to the kinetic energy in its magnitude. That means mgh is equal to a half mv squared. Now, this is what's really cool about it. Of course, we've got mass on both sides, so we can get rid of that. And that means that we can take this basic form of it here. Let's just say, let's call it 2gh equals v squared. You can call it whatever you want. I just took the 2 across there. But you can find a height from that if you want to know what the height of an object will go due to being thrown up with a certain velocity. That will of course be v squared over 2g. If you want to know the speed at which something will hit the ground if it's been dropped from a certain height, we can say v will be the square root of 2gh, and so on. Okay, so that's probably the two most useful versions of it. Okay, but really you just need to know that when one drops, that one converts to the other. If it's been dropped, if it's been thrown up, then it's the opposite effect, of course. But we can just get this line here and rearrange that as we need to. Okay, so as something falls, we can start to calculate the energy, or sorry, the speed of it as it when it falls to a certain when it falls a certain height.